Welcome to the Museum at MFIT's Material Evidence, Assessing Risk in Museum Collections Virtual Symposium. My name is Tania Melendez Escalante, and I am Senior Curator of Education and Public Programs. It is my honor to introduce Cheryl Podsiki, who will present the talk, Testing for Heavy Metals in Fashion Collections at MFIT. Cheryl Podsiki trained as an objects conservator and focuses her private practice on analytical testing for heavy metals that may be present in museum collections. We thank the U.S. Institute of Museum and Library Services, as this project is made possible by a grant from IMLS. We hope you enjoy the show.
Hello, everyone. I'm going to be talking to you about the XRF testing that we did on 165 objects in the fashion collections at the museum at the Fashion Institute of Technology, usually referred to as MFIT. I was on site for a period of 4 weeks in the fall, November 2021. Doing on-site testing, and then I do final documentation in my own office at home, because it takes about 3 times the time to do the documentation as it does the testing. So it was a wide range of artifacts, a wide range of materials, and actually spanned over 200-year time period from the 1700s to the 1900s. So it was a very interesting collection to test. This is me standing, this is Allison, and we're actually discussing how we're going to proceed on a certain object. We're going to be using an instrument referred to as XRF. It stands for X-ray fluorescence, and it's a handheld instrument. And the only takeaway I would like for you to see on this is that you always before using any kind of X-ray machine at all, you need to go over the radiation safety manual. The instrument is going to be emitting low level X-rays, so I'm not worried about that at all, but we still follow protocol. This is the instrument here that was used for this testing. It's manufactured by the Bruker company. This is the model is a Tracer 5i handheld XRF. It actually is used for a non-destructive surface technique, and for the most part, the results are qualitative, especially on heterogeneous substrates, which is what organic substrates, textiles, all fall into that category. There are, sometimes you can with homogeneous pieces be able to quantify, but in this case, we're just doing qualitative. The instrument will detect the elements that are on this periodic table. I'm bringing your attention to the one that's in blue here. That is the rhodium. That's from the rhodium 2. That is rhodium. And in the instrument, there is a rhodium 2. And that is where the X-rays are generated from. So I'm just going to do a brief overview of what's happening with the instrument, and then we're going to go on to the testing. So you can see that there's a detector here, and that part of the instrument is going to be hovering over or on the object, and then the X-ray is being emitted from right here where it says the X-ray 2. So what happens basically is the X-ray from the machine is going to emit an X-ray, a high energy X-ray that's safe but still low energy, and it needs to eject the electron in the lower shell. Eject that out, and here's the part to understand. When that electron shell is ejected out, the atom becomes unstable. It doesn't like being unstable, so it's going to send another electron from the next highest shell up. It emits an energy, a low-level energy. That is what the instrument is measuring. It's referred to as a photon, and it is actually X-ray fluorescence, and every element on the periodic table has its own characteristic X-rays for that, and that is what the machine detects, and that's what it's going to give for our output for reading. So the question becomes, to test or not to test, and do you need to test, and if you do, why and what and how? Identifying the reason for the testing is really important. Like, what is it you want to know? And then when you answer all those questions, you have to decide on the method. Is it really necessary to actually have a full analysis such as this with the XRF? Or are you just looking to see, does this object have arsenic on it? Does it have mercury or lead on it? And you can use the chemical spot tests, which are actually relatively much cheaper compared to doing an analytical, an elemental analysis on it. So there's also a possibility, maybe you just you don't have the ability to have testing done at all. And that is okay, because most hazardous collections actually can be managed for safety and health reasons, and also to manage the objects so that to keep them safe. So it's a matter of knowing the history or whatever the needs are, but there you have options. And you don't, if you don't think you can afford to have testing done, don't have the research ability to look into history of pieces, or just general history of pieces, have someone like myself. There are many of us who would come in, and if you'd like to have your collection observed, we could help you to just like, oh, you might want to put this over here and maybe just contain this. So it's just a helpful thing. So don't worry about not being able to test. This just highlights some of the 90 chemical compounds that Nancy Odegaard at Arizona State Museum and her team researched and uncovered. Over 90 different chemical compounds used in museums in the United States. And so what we are concentrating on are the heavy metals, in particular arsenic, mercury, and lead, but there are others. And also a non-metal, actually a liquid called bromine. This is methylbromide, because methylbromide was an insecticide that actually was used in several of the museums. Sometimes a little red flag will go up. Well, you know, those emission peaks, and I'll show you what I mean in just a minute, that might be a pesticide. So it's just important to know that. This is the methodology that we followed that I always follow for when I do XRF testing. That I have an annotated mapping. These are working documents that we write anything we need to write on. This is the XRF log that records all the instrument information and results. Very important, because you can go back by using this, especially if you were looking for a pesticide, you can actually see if there's a pattern of any kind of heavy metal that's going across. In this case, there wasn't, but we were able to identify different metals on different parts of the hat. And this is Kristen Robinson actually testing that hat. So all of that working information is going to end up in a final document that is going to have a front page that looks similar to this. Again, this is what I do. And what I want you to note is this hat was fabricated in the United States and made in 1943. That period of time, up until late 1940s, 1950s, many felt hats actually were made with mercury. It was using a process in manufacturing called the carroting process, that the mercury helped to like knit the fibers together. And indeed, this is the spectrum that shows the mercury. One of the things I want to point out is here. Remember in the beginning, I talked about the rhodium. That's from the X-ray machine, the X-ray tube in the machine. It generates a back scattering that is called Compton peak right here. So even though this is qualitative, I can tell between with this Compton peak being so low and the distance to the highest peak, that there is a lot of mercury here. I can't tell you how much is in there because we don't have the references for that right now anyway. At the museum, we don't have that. But you can tell a lot from having qualitative, the spectrum, reading the spectrum. So on this one, these are all still from the pink hat. I'm just going to quickly show you something. This was actually when we tested the velvet ribbon over the pink felt. Again, here's the Compton peak, high mercury, and over here we have high tin. The tin is actually coming from the velvet ribbon. We know that because there's no tin in the mercury, and the mercury is underneath that ribbon. Over here we have the light tan feathers that were measured. They're very low levels of mercury and lead, And that mercury is likely just from being picked up from the felt underneath. And those feathers, that particular group of feathers does not appear to have been had a pesticide treatment. Then this over here, we have a black, the grosgrain ribbon on the inside of the hat, which is over then, if you can imagine the inside. So that's actually laying over the pink felt. And it is the mercury that's still coming through because it's just a thin piece of ribbon. Mercury, these are mercury vats. You've heard of Alice in Wonderland, the Mad Hatter. Well, that is what can happen when you're inhaling all of that mercury vapor. It affects your nervous system and your spinal cord and your brain. And besides making you actually go a little crazy, it could kill you. So mercury mercuric nitrate was the compound often used for making felt hats. Not all of them, but it was very common. Mercury amalgamated mirrors are still around today. And as they break down, the compounds separate, and there's little mercury droplets that'll be at the bottom of the mirror. And this is, again, this is reasons for heavy metal. Why are there metals in collections? Well, there's all kinds of reasons. One is the manufacturer that we just talked about here. This actually shows mordants. Many mordants are metal salts. And mordants are added because they attach to the fabric, the fibers of the fabric, and then the dye attaches to the mordant, kind of gets a free ride in order to make the color of the fabric that you want. In the collection, out of 33 top hats, just men's top hats alone, we tested 10 of them. This one actually is made out of animal fiber, and it is high in mercury, which you can see here. Again, here's the Compton Peak for reference. High in mercury and high, this came out high in silk, because where we tested was not just the fiber, it was the fiber over the silk lining. So we're picking up both here. The XRF will detect in organic substrates, possibly down to like a centimeter or even deeper, maybe, depending on what the substrate is. On this one, we tested the front headband, which was the silk grosgrain over the animal fiber. Now this time we have the silk in is the lead, and then the animal fiber is the mercury. So you can tell by the spectrum just where these pieces are. Not always, but in this case we can. Then here we have the high lead, and that was the brown leather hat band. Again, this is one of 10 top hats that we tested. Interestingly enough, there were 9 black top hats that we tested, and we fully expected them, truly expected them to be mercury, but they kept testing arsenic. So finally, it just didn't make sense from our point of view. It was actually, they were labeled as being fur felt, but the fiber identification showed that it was not, that it was silk. And in fact, I think there were like 8 black silk plush, 1 silk weave, and then there's another one that actually was neither arsenic or mercury, and another one that was wool, and it indeed was mercury. So again, these are all manufacturer. This is coming from the manufacturer. This is not pesticides that we know of, with a possible exception here. I don't think so. This is the hat, the first hat that was tested, the first object we tested for me to be able to test out the parameters, like what filter did we want to use, what were the settings in general that we wanted to use. We changed depending on the object, and this one indeed was high mercury. This one, I can't tell you why the outside was arsenic and the inside was mercury. I'm not sure. We have to look into that. Maybe it was actually 2 different pieces of fabric. This was tested for high arsenic, the fur felt, and then this was high lead. So indeed, not all fur felt hats were had mercury in them. Again, this is manufactured. This is just to show the array of what was there. This has glass beads on it, arsenic and lead in that. That's very common for glass. Here's a silk plush that's not arsenic, it's actually lead. And these little leaves up here, oftentimes, we actually expected them to be arsenic. They in fact were lead and chromium on both of the examples that the museum had a test. So we're just going to go on. Now, there's also, besides manufacture, you might have natural sources, such as geological specimens that then, of course, are ground into mineral pigments. We have environmental, such as the ambient air, and almost every surface, if it's in your house, if it's in a museum, wherever you're at least in the United States, the XRF will typically pick up a very low level of lead, and that in all likelihood is coming from the ambient air, which is very sad, but it's true. And so we have the paint with lead. This is actually made from coral and plastic beads. I'm guessing that the mercury that showed up, it was high mercury, is likely from a vermilion pigment. And this is another way here that can be tested. I'm testing pigments there, not at this museum, but in another institution. And the instrument can be stood up this way, and then you can put small flat surfaces on there to test it. So now we're getting into tissue cell preservation and pesticides. So this where it's all red outlined, these are natural history specimens, as you can tell, but the circle areas are where typically heavy metals such as arsenic or mercury would have been inserted. The skin would have been opened, the metals would have been inserted. And the reason for that was to preserve the DNA for those. So here, this is a digital x-ray that was a courtesy of the Buffalo State University and Conservation Department. And all that solid white is arsenic that was in there. And that was they tested it with XRF, and then they did the digital picture. You might not be able to see it, but there are tiny little specks, white specks coming here. That is from the arsenic migrating through the skin and the feathers. That is over time, that is exactly what will happen to most pieces. I always tell people in a restaurant, try not to sit underneath a taxidermy specimen because all vibrations will start to shake that out. Here we have a botany specimen commonly preserved with mercuric chloride, which again, it's still going to off-gas. Mercury will off-gas its vapors, and that's the dangerous part about mercury. And so it's just don't stand over the specimens and then breathe it in. So again, Kristen is testing this is a bat head piece. I believe that arsenic is probably from a preservative or a pesticide. And I was testing, this is the bear claw, and they had a little bit of mercury on it. This, courtesy of Arizona State Museum, this is an actual artifact that was there as a Brazilian headdress. And that is all that white is arsenic. We believe it was arsenic trioxide. This is a piece of buckskin object. All of that white is arsenic, and it was tested, so we know that. Oftentimes you are not going to be able to see this. It's going to be in a solution. It got sprayed. It was a soap. You won't know unless you test, or if it actually shows some of the residue. The reason for pesticides, right here, whether it's fur, feathers, anything organic, you can see how this has been eaten. If in your collection you have older collections, like say from the 1800s to the mid 1900s, 1970, even into 1980, if those collections, such as the feathers and fur, are in pristine condition, a little red flag should run up in your mind saying, this might be treated. It might not be, but the only way you're going to know is to test. And if you can't test, make the assumption that it was treated, and treat it as such to keep yourself safe and the object safe. Something else, arsenic that was, and this was very commercialized, and it says right here, poison, right here. This was a company called Cyber, and it was a process called cyberizing. They used sodium arsenate to moth-proof your wool rugs, your clothes, and furniture. So that wasn't very, very comfortable, I'm sure, but no one really thought too much about it back then. So these are all from the museum, the MFIT. These are instances where it's really difficult to try to project a likely profile unless you have documentation that tells you something was made this way, this was actually had a pesticide applied. You can't say that for sure that it was, but you can make a pretty good estimate and try to project a profile. The felt hat was mercury, is likely from manufacture. The feathers and the bird were arsenic, likely from pesticide applied before it went on the hat. The feathers and the felt are kind of mixed in together, and it shows mercury and arsenic on both, but I wouldn't be able to specifically say where the source of that was. Again, this is actually a fake bird, but real feathers and felt hat. They mercury was found on both of them. Maybe it was manufactured the hat and pesticide on the bird, but we don't know that for sure. This one had high bromine peaks through it. So it could be from the bird's environment, but I would kind of err on the side it was likely a pesticide, maybe methyl bromide, which would have meant that all of the feathers, or if it was already attached to the mesh, the whole piece was exposed to the methyl bromide. And then these objects, we have a silk cape, and it was the fur that it tested for mercury. No, mercury was not on the other test that we did. On this hat, we have a felt fur again, but the peaks were lead and zinc and low lead. So again, you just don't know unless you test. There's black beads that were said to be jet, whether it was referring to the jet black color or real jet. Real jet is actually organic. The XRF will not detect it, but it did detect arsenic and lead and other heavy metals. Those beads are actually glass. So the white feather, again, has bromine on it, and high enough that it just sort of alerted me to, it could be that it had been, had an application, pesticide application prior to it being attached to the hat. Again, I want to point out, and I neglected to do that, but the dates all fall into when this was common practice. This hat, again, likely manufacturer, it was mercury. The feathers were also mercury. Is that from cross transfer from the hat, from the vapors, or were they treated? We don't know. The brown feathers actually had high arsenic content on them. They probably were treated with a pesticide application prior to going on to the hat. But again, without documentation, it's hard to tell. This is just to give you, it's because there's a takeaway at the end of this that I want you to have. This is actually a recipe that was used in 1925. This is a pound of arsenic trioxide and a half pound of, that was added to a half pound of sodium carbonate, and was put into 1 quart of water. The concentration was like 92 milligrams per milliliter of arsenic in that concentration. It was a real recipe that was used by John Rowley in 1925. He used to dip the skins in it, maybe antlers. So I used that in when I did a research project with wood, where I coated and immersed certain blocks of wood, soft wood. My objective was to see if we could, in a simulated sweat solution, remove the arsenic from the wood. Well, after intense leaching, we were able to. The only conclusion we could make is yes, most of the arsenic was removed. It was ended up in the liquid solution, but more importantly, where there wasn't arsenic, there now was arsenic, and that shows right here. This is another block prior to being leached, and this blue is from pH paper because it's following the sodium carbonate. This is the pattern where the arsenic traveled inside the wood. The takeaway is this: heavy metals and their salts migrate on a regular basis. So that has real implications for health, for mitigation, treatment, preservation, and cultural ceremonies, especially for repatriated objects where Native American communities may want to reuse those objects that are being given back under repatriation, but they could be really full of a pesticide and moving in and out. It really has very harsh implications. So I just want to end by saying awareness, knowledge, responsibility, always put safety first, always, for yourself, for your coworkers, for your visitors, and for the objects and the collections. One of the things we found, the XRF users way back in the beginning, like in 2008, I mean, it was in the early 2000s when it started applying, people started applying the XRFs to museum objects. But we needed somehow to be able to communicate with each other instead of reinventing the wheel every time. So this is a really excellent online resource. Anyone can go to it, anyone can join, and you can, there's a lot of information, like there's maybe technical issues, maybe like what do you suggest I use for this? I'm just starting to use this, what can I do? They're really very informative scientists that are on there. And I'd like to end by thanking everyone, all of you, everyone at MFIT, and of course the granting agency and Bruker, and our technical go-to person, Michael, and especially the conservation staff. I could not have asked for a group of 4 conservators to work with who were efficient and just made it a pleasure to test with. So thank you very much. And lastly, I'm leaving a slide with resources on there that also include that Rudolph Anderson with that high concentration of arsenic recipe is. So once the symposium is over, then people will be able to come and look at the slides if they wish to, and they would be able to freeze it and get all that information. So thank you very much for your time, and I hope I left you with some good takeaways. Thank you.